Welcome to this video on the DeBroglie Hypothesis and the Davison-Germer experiment. We're going to get into the details of what those two things are in a minute, but first I want to take you back to the photoelectric effect, and we will tie it all in together in just a few minutes. The photoelectric effect, which is this experiment that we keep coming back to, is so foundational that many of the ideas presented there in that experiment are going to be necessary to understand the DeBroglie hypothesis and then the Davison-Germer experiment, which supported that hypothesis. Also, I just want to make a quick note here so I don't forget that G.P. Thomson, the British physicist whose dad was J.J. Thomson, who discovered the electron, he's also attributed with independently collecting data in his experiment that also supported the DeBroglie hypothesis, and so I just wanted to recognize him there. With the photoelectric effect, we saw a few main ideas that were crucial to our understanding of how light or electromagnetic waves are behaving and interacting with matter. The first idea is that it supported this idea from Max Planck that frequency and energy are directly proportional. There's a strong relationship between the two. We also saw through this that the energy could be related to the momentum of the photon as well. In addition to the photoelectric effect showing these relationships and showing the interaction between the matter and the electromagnetic waves, we also want to include here this idea from Compton scattering. These ideas are going to become very important in us connecting what DeBroglie is going to propose, and which sounds crazy when you first think about it, but as we've seen, the evidence supports the craziness. So what I want to do here is relate the momentum to the frequency, or the momentum to the wavelength of the wave. So I'm going to set these two equations equal to each other, have something that looks like this. Now we have to remember that Einstein proposed this idea of the little energy carriers within the light as photons. And we have to be sure here to think that photons have energy, and so when we think of mass energy equivalence, like in the equation E equals mc squared, what we have to do is kind of break our attachment to what we refer to as mass. When we talk about mass energy equivalence, we say that you can really measure the energy of a particle or a wave or something like this in terms of energy, but you can also refer to it in terms of mass. And mass, again, as I've said in many videos, particularly in the mechanics videos, mass is not necessarily a measure of the amount of matter, but rather a measure of something about the resistance to the change in momentum. And so if you think about it from that perspective, we can think of the fact that photons can have momentum because they have energy, not only have momentum because they have mass, because mass and energy are interrelated. So when we look at photons, we're looking at their mass, so to speak, as being in the form of energy amounts rather than being in the form of mass amounts, because mass and energy are interchangeable in some way. More on that later. So here, when we get back to this equation here, I'm going to set in this equation here c is equal to f times wavelength. Okay, that speed of light is equal to frequency times wavelength, like this. And what I see is that frequency will factor out, and I'll be left with Planck's constant is equal to momentum times wavelength. And this is where the DeBroglie hypothesis is going to pick up. So Louis de Broglie was getting his PhD in physics in the 1920s, and at that time, what he was proposing in his thesis was that not only do photons, also these little electromagnetic light particles, so to speak, and I say that in quotations, not only do they have some sort of momentum and wavelength and can exhibit wave-like properties like interference and those sort of things, but he suggests that matter itself could also have wavelengths associated with the matter. And so he calls, we refer to these now as de Broglie wavelengths. Now, you heard me correctly. What he said was that matter, so little particles, can have a wavelength, which sounds very odd. And this is really some of the very important birth of quantum mechanics and our understanding of physics from the perspective of waves, and is where Erwin Schrödinger comes into the picture. More on him later. So we're going to take a look here and say that this relationship is true. Now, another way that we could look at this relationship is we could say that the wavelength is equal to this constant h over p. So Planck's constant, remember, is a very, very small number, and it's going to be important in us understanding why we don't necessarily pay attention to matter wavelengths, because they're so small. And we're talking here on the order of magnitude of times 10 to the negative 34th joule seconds. So this is a tiny value here. Now what he proposes is that let's not look at photons anymore. Let's look at actual particles. So we're going to have this little tug of war here between photons, which are these light energy carriers, and electrons, which are also energy carriers, but they are moving in terms of having mass, and therefore their momentum's coming from their mass. Photons are having momentum that's coming more from the perspective of looking at, rather than mass, looking at energy. So what DeBroglie suggests is that, okay, if nature is symmetrical in this sense, like it is in most cases, if light can be a photon, and a photon can have energy and momentum, then why can't an electron have wavelength and frequency? So why can't a particle have wave-like properties if a wave can have particle-like properties? And so what he does here is really just sets in that p, momentum, is equal to mass times velocity here. Now again, we've changed from having p be an energy-related idea to a mass-related idea. And he shows this idea in the following way. Let's pretend that we have somebody throwing a baseball. Let's say that the baseball has a mass. I'm going to make this kind of silly. The mass of the baseball is going to be 1 kilogram. Okay, so the mass here is 1 kilogram. And the velocity of the baseball while it's being thrown, let's say it's about 28 meters per second. So if I go ahead and I plug in these values over here, I get h is 6.63 times 10 to the negative 34th divided by 28. That's still really small. And so what he proposes is that the wavelength of the baseball is equal to some really tiny number, and that is why we haven't actually witnessed particles, aka electrons, behaving with wave-like properties. Now when we talk about wave-like properties, what are we describing? Well, all the things that we discussed within optics. So we know that photons, or light in general, those can reflect off of surfaces, they can refract as they pass into new media, they can also diffract, move around things or through little openings, and then they can interfere, as we saw with the double slit and other slit experiments. But we don't usually see particles doing that. When you walk through a door, you don't diffract through the door and show up, in the room in multiple places. You stay all as one. But why he proposes this idea is he says that actually, yes, electrons can do these things, particularly here we're looking at diffraction and interference, but we don't usually see big things like a baseball of 1 kilogram. We don't see big things diffracting and interfering because their wavelengths are so tiny, as you can see would be the result of this calculation. And remember that in order to see diffraction, or in order to see interference, the wavelength of the light has to be pretty close to the gap spacing of the thing that you're diffracting through. So we looked at the idea that the gap spacing between the crystal particles let's say they're 10 to the negative 10th meters apart, or an angstrom apart, you would see interference there because the wavelength of the light is approximately the same as the gap spacing. If the wavelength is way too big, then you don't see the diffraction because it won't actually diffract through those little openings. But electrons moving at very high speeds, so as v goes to a really big number, and m, electron mass, which is on the order of magnitude of times 10 to the negative 31st, if that goes down and this goes up, and this denominator becomes very small compared to Planck's constant, we see that we will start to get wavelengths that are actually closer to gap spacings in molecules. So when we come back in the next part of this video, what we want to do is take a look at the experimental evidence for this whole idea that electrons can diffract and interfere.